Today, we'll be finding critical points in Calculus 3. So compared to Calculus 1, in Calculus 3, you need to find a derivative for two things rather than just one in order to find a critical point. And also keep in mind, critical points don't necessarily have to be local maxes and mins. They can be something called a saddle point, which we will cover in my next video. Probably. But let's go ahead and start off with our questions. So for x squared plus y squared minus 4x minus 6y plus 8, at this function, what are the critical points, or the points that are potentially our local mins and maxes? Well, in order to find that, both the x and y partials have to equal 0. So let's go find our x and y partials first. So the x partial for this equation is 2x minus 4, and our y partial is 2y minus 6. And we have to set both of these equal to 0. And so for both of these equations, let's go write them down somewhere else so there's less distracting clutter. When are both these equations equal to 0? Well, the only time when this equation is equal to 0 is when x is equal to 2, and the only time when this equation is equal to 0 is when y is equal to 3. So our point is just simply 2, 3, where our x is equal to 2 for the 2 value in our coordinate point, and 3 is equal to y for the y value in our coordinate point. Now, not all problems are as simple as that, and you'll see soon. But for this next problem, x to the power of 3 minus 3xy plus y to the power of 3 is equal to our function f of xy. So let's find, good, as I said before, let's go find our partials. So our x and y partial derivatives are 3 times x to the power of 2 minus 3y, and 3y to the power of 2 minus 3x. So what we can do here is set these both equal to 0, and technically I guess we could solve this as a system of equations, but typically when you have exponents like x to the power of 2, it's going to be a lot harder to keep things around. So I'm going to be using some tricks that maybe you can learn from. So I'll factor out 3 here, still set this equal to 0, and I'll factor out 3 in the bottom equation as well, and set this equal to 0. So I'll divide 3 on both sides, and this is what we get. X squared minus y is equal to 0, and y squared minus x is equal to 0. So what immediately sticks out? What points will hold both of these equations true? Well, 0, 0 sticks out to me the most because, well, 0 minus 0 is equal to 0. But what other points stick out as well? Well, we can simplify these equations, can make these equations also equal to x squared equal y, and y squared equal to x. So what points hold these true? Well, simply 1, 1. Because 1 squared is always equal to itself. And 1 squared of y is equal to x as well. So these are our two critical points for this function. And all we did was just maybe use some math tricks, use some numbers. There's no direct steps for all of them. The steps that I'm showing you right now are the easiest route that you can take. I guess you can solve this using substitution, but that would be a lot more complicated and annoying to do. So these are just the steps that I'm showing you that are kind of like shortcuts. So for our next function, e to the power of x times sine of y is equal to our function f of xy. Now let's find our x partial and our y partial. So our x partial for this is e to the power of x sine of y, and e to the power of x cosine of y. And both of these need to be set equal to 0, and I'll separate these equations with our partial symbols. E to the power of x cosine of y is equal to 0. Now notice this. E to the power of x can never equal 0. And the reason why is if you exponent anything inside of an exponent can never equal to 0 unless if it's, well, negative infinity. But then again, that's still only, I guess, I'm not necessarily sure, I'm not a mathematician, but I guess that would still not equal 0. Actually, would it be like positive 0? Like infinitely close to 0? I don't know. Go ask your math teacher. But this equation just turns out to be sine of y is equal to 0, and cosine of y is equal to 0, because at no time can e to the power of x equal to 0. This will always be some positive number. Now that we have this, take a look at this problem. It never works. Both sine of y and cosine of y, using the same variables of y, can never both equal 0 at the same exact time. So the answer is a big fat none. No critical points. So sometimes that can happen when you have no critical points, but I guess hopefully most of the time your teacher isn't giving you problems like that. Because those that one kind of messed me up. I had to double check that when I solved that before this video. So for our next function, it is x to the power of 4 plus y to the power of 4 minus 4xy. Let's go ahead and find our partials. Our x partial will be 4x to the power of 3 minus 4y, and our y partial will be 4y to the power of 3 minus 4x. We can go ahead and factor out our 4's. So equal to 0. We can go ahead and factor out our 4 for the bottom function as well. Set this equal to 0. And if we divide both sides by 4, 4 just gets eliminated. So this just goes away. And our function turns into x to the power of 3 minus y is equal to 0. X to the power, not x, y to the power of 3 minus x is equal to 0. So we can actually move these both to each side. So let's rewrite our function over here. Equal to y, and y to the power of 3 is equal to x. So at what points do both of these equations hold true? Well, again, 0, 0 sticks out. 1, 1 sticks out similarly, like 2 questions before. And this time we have 1, negative 1, and negative 1. Because negative 1 to the power of 3 is also negative 1. And negative 1 to the power of 3 is also negative 1. So negative 1 works here. And these are our 3 critical points for this equation. Okay, this next problem is a little harder than the other ones, and typically you're not going to see a problem like this because, well, you have to use some fancy tricks in order to be able to solve for this one. So for this, let's go ahead and find our x partial and our y partial. Our x partial is 2xy plus y to the power of 2 minus 3, and our y partial is x squared plus 2xy minus 3. Now if we set both of these equations equal to 0, a neat thing that we can actually do is subtract both equations from each other. And this just makes our equation simpler to solve. So we put these in parentheses. We're subtracting this. This is the f of x function, this is the f of y, and this is our f of x function, and this will be our f of y function over here when I write it down. X squared plus 2xy minus 3 is equal to 0. We can actually subtract both these equations. Now, most of the time you're not going to need to do this, and most of the time you'll just, I guess, solve for things, right? But you can subtract both of these equations using elimination. You can get rid of this guy, this guy, this guy, and this guy. And using elimination, all you get left off with is something simple. Y squared minus x squared is equal to 0. Therefore, y squared is equal to x squared. Therefore, y is equal to plus or minus x. Now, if we plug in our value for x here, so if we substitute back in our x into some of our function, which one will you pick? Oh, you picked the x partial. Oh, let's plug in x for y in our f partial. So our f of x partial turns into, we're substituting positive x first into our y value, squared minus 3 is equal to 0. Now that we have this, this turns into 2x squared plus x squared is equal to 3, and 3x squared is equal to 3. So x is equal to plus or minus 1 in this case. Now that we have our x values that could be possible, let's go ahead and solve for our y values here. So if we plug back in, well, we actually, never mind. Let's first solve for this. I'm skipping steps here. Move this to the top. Let's plug in negative x in this case. So let's plug in negative x plus negative x squared minus 3 is equal to 0, because y is equal to plus or minus x. So we have to plug in negative x here. So this turns into negative 2x to the power of 2 plus x to the power of 2 is equal to 3. And this turns into negative x Yep, negative x is equal to 3. And in no situations is this possible. So negative x is just ignored. So far we have x is equal to plus or minus 1. Now we have to solve for our y values. So when x is equal to plus or minus 1, let's go plug it back into this equation up here. So for f of x, let's go plug in plus or minus 1 for x. And we'll start off with 1. So we plug in 1 into our f of x function for x. We get 2y plus y squared minus 3 is equal to 0. And in this case, you can actually factor this out. Can you? Yes, you can. Y plus 3, y minus 1 is equal to 0. So y is equal to 1 and negative 3. And for the next case, let's actually shrink this. Of negative x, we'll plug in negative x here. So we get negative 2y plus y squared minus 3 is equal to 0. We can factor this out again. This is y minus 3 this time. Y plus 1 is equal to 0. So y is equal to 3 comma negative 1. Here's the thing about this though. Your y values could be wrong. So we actually used, okay, let's keep this in mind. We used negative 1 is equal to x here, and we use 1 is equal to x here. If you plug back in 3 and negative 1 for this equation, so if you plug back in 3 for y, so if you plug back in, let's change the color. If you plug back in 3 for y, and you plug back in x is equal to negative 1 here, does this equation hold true? Let's find that out right now inside of my head. 1 plus negative 6 minus 3 does not hold true. So what does that mean? Well, in order for our equations to hold true, both the y partial and the x partial have to equal 0. And when, at this point, negative 1 for 3 for this equation here doesn't work. So our doesn't work. This y partial does not equal to 0 when y is 3 and x is negative 1. So what does that mean? This 3 gets wiped out. Plug negative 1 for x and negative 1 for y, so this is our point here, up into this equation here. Does that work? Yes, it does, because this turns into 1, this turns into 2, right? So this is 1, technically 1 plus 2 minus 3. That equals 0. So at point negative 1, negative 1, that is one of our critical points. So we have to make sure that both of these equations hold true with our values that we get using algebra. How about for this problem right here? When x is equal to 1, does negative 3 work? Plug that back into f of y, and you'll see that 1, negative 3 does not equal to 0. So we can actually just go ahead and erase this here. So 1, 1, and 1, negative 1 are our critical points for this problem. So to recap, all we did was find the x and y partials. We set them equal to 0 and solve for the system of equations or use some algebraic manipulation or some number understanding in order to solve for the equations. Sometimes your answer can be none for critical points. And in this case, you'll do a lot more than just look at it and be able to see it. But that's it for today's video. If you have any questions, put it down in the comment section.